Welcome back. I am so glad you've joined me again. Go ahead, settle in, get comfortable, and maybe take a nice deep breath. In our journey through General Emergence Mechanics, or GEM, we've been exploring some absolutely incredible, profound ideas about why anything exists at all. Today, in Lesson 4, we're unpacking the three magic tools that control persistence. I really like to think of this as a story about the quiet mechanisms that hold our universe and, honestly, ourselves together. So let's build a really clear, intuitive picture of how persistence actually works. Just gently recapping what we looked at in Lesson 3, we discovered that persistence is, well, it's kind of this quiet superpower that lets things stay real. It's the literal difference between a fleeting, virtual blip of energy and a solid, stable particle, or a planet, or even a person. But that leaves us with a really beautiful, lingering question. How do things stay together? By what exact mechanism do things manage to hold their shape in a universe that is just constantly buzzing with noise, stress, and disruption? Okay, let's dive into this. According to General Emergence Mechanics, the secret lies in a rule of three. There are exactly three parameters, three magic tools, if you will, that dictate stable existence. And I want to be clear, these aren't just abstract, purely mathematical concepts. They are the fundamental axes of what we call a coherence shell. You can think of a coherent shell as a protective bubble of stability. For anything to survive inside that bubble, these three tools have to work together perfectly. Let's look at them one by one. The first tool is depth, represented by the letter D. In strict physics terms, this is the energy barrier to escape the local coherence shell. But let's bring that down to earth a bit. Imagine you're building a sandcastle on the beach. Depth is basically the size and depth of the protective moat you dig right around it. It represents our overall resilience. It dictates how large of a wave, or, how big of a stressor, the system can absorb before the whole structure just gets washed away. If your depth is high, you can withstand a massive amount of disruption before breaking. The second tool is stiffness, represented by the Greek letter kappa. Now, while depth is about your ultimate breaking point, stiffness is all about the immediate pushback against a disturbance. Going back to our sandcastle, stiffness is the actual quality of the sand itself. Is it that perfectly wet, densely packed sand that holds its sharp edges when you tap it with a plastic shovel? That right there is high stiffness. It's the immediate elastic resistance to perturbation. In our daily human lives, it's our immediate adaptive buffering, how quickly we brace ourselves when something totally unexpected hits. And the third tool is viscosity, or the relaxation timescale represented by the letter tau. This one is simply the ability to recover from a disturbance. Think about it. If a wave breaches your sandcastle's moat, how long does it take for the water to completely recede so you can rebuild? Or, to put it in much more human terms, if you get stuck in a really frustrating horn-honking traffic jam, how long does it take your blood pressure to return to normal once you finally get home? High viscosity means it takes a very long time to bounce back. The distortion just kind of lingers. Low viscosity, on the other hand, means you snap back to a calm baseline almost instantly. Section 1. Working together, the sandcastle of stability. So, the crucial point here is that these three axes, depth, stiffness, and viscosity, are a tightly coupled system. They absolutely must work together perfectly for things to stay stable, whether we're talking about a literal sandcastle or a human body. Now, what's really interesting about this concept is how it maps out exactly what goes wrong when these tools are out of sync. Think about the brittle collapse scenario. That's high stiffness but low depth. This is a system that pushes back hard but has zero underlying resilience. It's like a dry sandcastle. It seems super solid, but the moment the stress is just a little too much, it doesn't bend. It just undergoes a sudden, complete collapse. Contrast that with creeping distortion. That's low stiffness with high viscosity. This system has almost no immediate pushback, and it takes forever to recover. It's exactly like a lingering bad mood that slowly works your entire week. The stress just stays trapped inside the system. Section 2. Real-life connections between stability and stress. When our three tools get worn down by the environment, GEM formally calls this persistence drift. But let's be real, you and I know it by a much more familiar name. Just having a really, really bad day. Let's actually see how this builds right into our own biology. We can map these exact GEM concepts directly onto human homeostasis. Notice how depth becomes our absolute resilience to physical or mental breakdown, basically how much exhaustion or illness we can fight off before we crash. Stiffness acts as our immediate adaptive buffering, like your heart rate spiking to supply oxygen when you're startled and then quickly regulating. and viscosity is the speed at which we recover and heal. When we are chronically stressed out, our biological viscosity gets dangerously high. We just can't seem to settle back down.
So, how does biology naturally solve this buildup of stress? Well, it forces a reset. In GEM terms, it forces the system to return to a stable basin. For us, returning to that stable basin is quite literally like getting a good night's sleep. Sleep is our body's ultimate built-in natural mechanism to completely restore those three persistence axes after a long day. It lowers the environmental noise, allowing our biological viscosity to decrease so all that trapped stress can finally dissipate. It deepens our resilience mode, getting us ready for the next day.
Section 3. Building the sleeping suit. The biological coherence pod. Now imagine if we could engineer an environment to perfectly support this natural sleep process. Conceptually, we are talking about building a high-tech resting chamber, a sort of suit to gently support all three axes while we rest. And this brilliantly illustrates a core philosophy of this entire framework. To quote the source material directly, biological well-being is not static equilibrium, but robust persistence. Being healthy doesn't mean you are frozen in place, perfectly still, never experiencing any stress at all. Honestly, that's impossible. Being healthy means you have the robust mechanics, the depth, the stiffness, and the remarkably low viscosity to absorb the shocks of everyday life, bend without breaking, and gracefully bounce back to your fully functional self. So how would this coherence pod hypothetically function? Well, it works in 3 key steps. First, it defines a low-noise local shell around the body, meaning it aggressively quiets the acoustic, thermal, and mechanical disruptions around you. Second, it senses your biological state and motion, acting as a smart, closed-loop system to monitor things like your heart rate. And third, it applies gentle, structured modulation to aid recovery, maybe slight thermal changes or very subtle vibromechanical stimulation. It essentially acts as an environmental shock absorber, lowering those physiological gradients so your body's viscosity can drop and you can properly, deeply heal. It literally engineers stability. It's such a beautiful, empowering way to look at our own health, isn't it? As a constant, dynamic maintenance of our persistence tools. We've seen how depth, stiffness, and viscosity hold us together, and how sleep, and maybe even engineered environments, might help maintain them. But that leaves us with a pretty vital question for our next explainer. What happens when our biological or physical environments push us just a little too far? What happens when we lose our balance, these axes degrade, and our coherent shell actually begins to collapse? And much more importantly, how do we fix it? Well, we'll explore exactly that in Lesson 5. Until then, stay curious.